So this is a second week lecture. In this live session, we are going to discuss the reaction mechanisms diagram. That is, we will discuss later. And in previous class, I have covered already the different types of carbocations, carbanion radical reactions, and stability, and how to write acid catalyzed reaction, base catalyzed reaction, and basic concept of mechanisms in organic chemistry. So today we are going to discuss the reaction coordination diagram. So what is a reaction coordination diagram? Have you heard about this reaction coordination diagram before? So I'll tell you that the reaction coordination diagram is a graph that shows the relationship between the energy and the reaction progress. That means your energy required for the reaction and energy of the reactant and the energy of the product. So the relation is shown by the reaction coordination diagram. So which information the reaction coordination diagram is giving? The relative energy of intermediate, reactant and product, and the stability of the product, and amount of energy is required, that is relative energy. So I hope all of you know the definition of reaction coordination diagram. So here I have two examples. The first reaction coordination diagram I am going to explain here. So on y-axis we always have a potential energy. We can write energy also, and on x-axis we have a reaction coordinate. So suppose A is our reactant. We are doing the reaction between A and C. So when A is undergoing reaction, it requires some amount of energy to reach the transition state. This hill point, this top point is known as transition state. Transition state means it's undergoing some transition to get converted into the product. That's why it's called a transition state. And to reach the transition state, some amount of energy is required, which is also called as activation energy. Activation energy. Which is also denoted by AE. Then after activation energy, after reaching the transition state, if the reaction is single step reaction, single intermediate is not forming, that time it will convert it to product directly. So the best example for this type of reaction is SN2 reaction. I will give one example. Like suppose we have alcohol. In last lecture also I have given SN2 reaction example. So today also I am going to give the same example. Suppose we have bromomethane. Bromomethane. Correct? Now SN2 reaction is taking place. This is our reactant. Suppose this is our A reactant, and the base is wait, base is coming here OH minus. Now what will happen? It will attack on this carbon. Correct? So in transition state, so what will happen in transition state? Oh, we have to show the bond breaking and bond making together. Br H H and H. So this step is your transition state because the energy is very high. This is dotted line. That means this bond breaking is taking place here. Bond formation is taking place. So this is the transition state, and energy is very high because this is not the stable intermediate. Stability is always inversely proportional to the energy. If stability is more, then energy is low, and if energy is very high, that means the stability is very low. So here you can see this is our transition state, and after one step only we are getting product. So it will become our product. So because this is a single step reaction and there is no intermediate, this is just a transition state, no intermediate. So it's called a SN2 reaction. And here from this diagram we can say the activation energy for transition state is delta G. And after transition state, when it will be comes under transition state, it can be undergo both side. It can suppose our transition state is here, this one, so it can either go to A side or C side. But you can see here the energy of C is less than reactant A. That means C is more stable. So the more stable side should be a major product. So that's why it will go through here and it will give a product C in major yield. So I hope you got the terms and everything in first coordination diagram. Then we will discuss the second one. So this second reaction coordination diagram is resembles SN1 reaction. So as I told you, in SN1 reaction, first carbocation formation is taking place, then carbocation is trapped by other nucleophile. So because here we have intermediate, that's why here we have two transition state and intermediate. So this I'm just giving an example of SN1 reaction, but there are different types of reaction comes under this reaction coordination diagram. So what happens here? Suppose we have here reactant R, product P, and intermediate I. So our reactant is required some amount of energy to reach the first transition state. This is TS1 and this is TS2. Okay. So it requires some energy to reach the transition state 1, and after that it will release energy to get the intermediate I. Now you can see here I is in equilibrium with R. Very slight difference of energy is there, so we can call it's in equilibrium with I, correct? Whereas product is more stable and energy is very low for product. So when intermediate we will get here, after this getting this intermediate, it can go back to reactant also and to product also. But here you can see that the transition state 2 TS2 is the energy is required for reach transition state 2 is low compared to the transition state 1. Energy requirement is less here for transition state 2. So obviously it's a simple logic only for ourselves also. If we need less energy, we have lift and stairs. What will we will do? We will go by elevator only, lift only, and stairs we will not choose. Same case of here also. Compound will choose the same way. They will choose the smaller hill. Means suppose we have want to go larger hill and smaller hill, we will choose smaller one. Same case is here also. So because transition state is low here, energy is low, intermediate will prefer to go through this way and it will give majorly a product. It will give a product. And here transition state 1 is high, that means activation energy for reactant to transition state 1 is high, that means it is a slow step. And slow step is also known as reaction limiting step, or we can say a rate determining step. Rate determining step. That means rate of the reaction will depends on this step because it has high energy. So always remember that always the transition state with high energy will show the more reaction time. That means it's a slow step and that will become your rate determining step. Everyone is clear here? Any question regarding this thing? Sorry, activation energy. Okay. Activation energy is the energy required for reactant to reach the transition state 1. That means the energy of difference between the energy of reactant and transition state. That is called activation energy. Okay, it's denoted by EA also. In some textbooks you will see EA, that is called activation energy, and delta E means the difference between energies, activation energies. Got it? Okay. Now we have some examples of reaction coordination diagrams. Here we have three types of coordination diagrams. Here I have discussed two types, two hump and one hump. Here we have two humps diagram but with different types. So can you find out the difference between these three diagrams? Okay, now first find out the difference between first and second one. These two diagrams. Is there any difference? Yeah, where you will see here in first case, your reactant energy and intermediate energy is at same level, nearly a same level. As I told you, it's in equilibrium. Equilibrium means when it will convert it to intermediate, quickly it will get back to reactant, and this conversion will takes place throughout the reaction. So reactant will convert it to intermediate, and intermediate will get back to reactant also in same reaction. So this is called a equilibrium, equal energy. And where you will see here the reactant required less energy compared to the second step. Here in these two reaction coordination diagram, the difference is here only in reactant and intermediate energy. I will explain one by one. So here reactant required this much E1 activation energy to reach the transition state 1, and then it will get converted to intermediate I. After getting intermediate I, what will happen? It will require more energy to reach the transition state 2 compared to transition state 1, and then it will get converted to product. So the energy required, that is here E2, is very high compared to transition state 1. So which one will be your rate determining step? I have just explained in previous slide. Yeah, second step. Correct. Right. Second step is your rate determining step, and when it will cross this barrier, this energy barrier, and get converted to product, then it will become not possible to get back to intermediate and reactant. So that's why your product is more stable, and once the reactant is converted to product, it will not get back reaction, that is irreversible reaction. So this is the first case where rate determining step is transition state 2, energy required to reach the transition state 2. Now in second case, you can see here again we have two humps. The first transition state energy is less compared to transition state 2. So reactant is required even amount of activation energy to reach the transition state 1, and then it will get converted to intermediate 1. So whenever you are having a two-step reaction, only that time you observe these two hump type of reaction coordination diagram. In single step reaction, you will observe only a single hump like structure, this one diagram. So here we have I. Then after the I formation, I is intermediate, which is less stable compared to reactant. So but because the energy difference is very less compared to product, if you will compare the energy difference between I and R and product, you will see here energy difference between I and R is less compared to I and P, correct? So that means intermediate I is more in equilibrium with reactant R. So it will get quickly converted to reactant, and it will be easier because transition state is also low. The energy required to cross this barrier is also low to get the R. Now the in second step, transition state 2 is has a higher energy. That's why, because it's a higher energy, E2 will become our rate determining step. This step is our rate determining step, and again it will get converted to product. So I hope all you got this one also, this diagram. Now third diagram, what will happen here? Can you explain, anyone? What information do you get from this third diagram? So if we'll see here, we have reactant again here, but intermediate, the difference between intermediate, energy of intermediate and reactant is very high, correct? High. And when high energy intermediate is there, that means the intermediate is very less stable, very less stable. Now from reactant to reach intermediate, transition 1 hump will be the barrier for crossing this hump. So the activation energy for reactant is high here compared to the first and second diagram. Now after getting intermediate, you will see transition state 2 and transition state 1 have very less energy difference, correct? Very less energy difference. That means it's almost similar or in equilibrium, as we have told in second diagram we have done here. So the equilibration is there in transition state 1 and 2. That means after conversion of intermediate, it can either go on uh, TS2, that is transition state 2, or transition state 1 with same kind of uh, energy. That means it this reaction is faster compared to this one, because this second step is slower, but here it is not the case, and it will get converted to product. So here you can see I is steady stable, as I told you. It's a less stable, and it can go either TS2 side or TS1 side. So either it can get converted to reactant or to get the product, but product chances are high because product is more stable compared to the reactant. So that's why intermediate will become our steady state, means less stable, and it can go either side. So this is a third type of coordinate diagram. So I hope all of you are clear here. Any question? Yes, anyone? Okay. So now we will talk about Hammond's postulate. What is Hammond's postulate? So as you can see here, Hammond's postulate state that the transition state of a reaction, this transition state hump in a transition hump is called as a transition state. So it's resemble either the reactant or the product, whichever is closer to the energy. So suppose here our reactant is there and this hump here is a product, right? And we will cross the line between here, center. Yeah. So if I will divide this x-axis into two parts, this distance between reactant and product by half, then can you see this transition state is on which side? It is on reactant side. So this is the meaning by Hammond's postulate. So according to the Hammond's postulate, the transition state of the reaction resemble either the reactant or the product depending on whichever is closer to the energy. So here also if you will see here, this is closer to the product. So the transition state structure will resemble the product. Here transition state structure will resemble the reactant. So in an exothermic reaction, this is the first case where we have example of exothermic reaction, and the transition state here is closer to the reactant compared to the product. right? Therefore, huh. So the transition state is closer to the reactant. So this is an exothermic type of reaction which resemble the this transition state is resemble more to the reactant. Means structure and stability will be structure will look like the reactant only. And here we have transition state in second case. This is an endothermic reaction and product look like sorry transition state look like product. So these are two different type of reactions. So what is exothermic reaction? Have you heard about it? Or endothermic, difference between these two reactions? Yes. So delta H is negative, or delta G, Grubsky energy also is negative. So this is the case here, and this is the case here. So the reaction, if you are doing a reaction in a lab, that time you will observe that the exothermic reaction is become very the temperature of the reaction is rise immediately after adding the your reactant, other reactant. So you will observe that heat is evolved from this type of reaction, and this type of reaction get cooled down. So some reactions get cold and some get hot. This exothermic reaction, that means it will evolve heat. So that's why the transition state change both the cases. But the most stable product will be get by exothermic reaction only. You can see here product is stable in an exothermic reaction case, whereas in endothermic it is less stable. So I'm not going in detail with these type of reactions, but for right now you just remember this delta H is less in exothermic reaction, and for endothermic reaction delta H is high, more than 0. Now we have one example here for Hammond's postulate. So here you can see reaction. This alkene reaction is undergo substitution reaction with HCl. So here which transition state is stable we have to see. So first, because this is our tertiary carbon atom. This one is tertiary carbon, and the because the tertiary carbocation is more stable, I have discussed in previous class. So the carbocation formation will take place at this carbon only, because here it is primary and this one is tertiary. So tertiary is more stable. So then here tertiary carbocation formation is taking place. So this is our transition state. Our transition state is this tertiary carbocation. So when alkene is here and it undergoes reaction, you can see here this is a exothermic reaction. Sorry, this is a endothermic reaction. You can see the distance between here. So because it's slightly that side, endothermic reaction, by you can see here product is less stable than the reactant also, and your carbocation is a intermediate. Carbocation formation is your intermediate, and transition state is a this concerted structure, as I shown in a SN2 type of reaction. In previously I have shown here SN2 type of reaction, dotted line. This is our transition state. Same here also, our transition state is bond breaking and bond making simultaneously it will show. So this is our transition state. Then because tertiary carbocation is stable, that's why the hump will goes down and it will show a product. But because it's a intermediate and that's why it's less stable compared to the reactant. Then it will further undergo nucleophilic substitution reaction with Cl minus. So because it will require less energy then. Now, which one is your rate determining step? So this is the first step. And according to the uh, Hammond's postulate, if we will see this transition state, it will more uh, closer to product. That's why it will look like a product only. It will not look like a reactant. So this is a Hammond's postulate. Now, next we will discuss the kinetic and thermodynamic products. So I hope all of you have watched the MEMS lecture, which is available on YouTube. So I'm just giving a revision type of class, and after that we will solve some questions based on these type of concepts. Now, kinetic versus thermodynamic products. So what is the difference between the kinetic and thermodynamic product? So here you can see that I have drawn two different humps, transition state, that is one is green and one is blue. So the kinetic product is a product that forms faster, and the thermodynamic product is a product that are more stable. So we have starting material here. Now the first green one, see here green one, it is going to this transition state 1 TS1 with activation energy EA1, and then it's get converted to the product P1. While the second case, you can see here activation energy is more and transition state is higher compared to the TS1, and then it goes to the more stable product P2 compared to the P1. So the first green case is your kinetic control. I will explain how. This is your kinetic. P1 is kinetic product and TS1 is a transition state for kinetic product, and the TS2 is thermodynamic. Okay, how is thermodynamic and why is kinetic? So for starting material or reactant, energy activation energy means energy required to reach the transition state 1 is very less. That means it can quickly uh, cross this barrier, right? It can quickly goes to this hump. Suppose we have two hills and one is shorter and one is larger. So on shorter one we can climb easily compared to the other one. So here it will easily converted to TS1. It will easily cross this barrier fast. So this to reach this transition state, the time will be faster. So this step is fast, and it will get converted to product, correct? But whereas the second case, transition state is 2 TS2 is high, that means energy is required more, that means it will take more time, correct? So the time required for this one will be more compared to the kinetic one, so this step will be slower. But after reaching this step, it will get converted to more stable product. So how we can get these two different type of product in same reaction? Suppose because energy of the reactant energy of the transition state one is less, that means we require less energy to reach this one. So this type of kinetic reaction can be done at low temperature. Low temperature means it is not the energy is not required to reach the TS1. That means at low temperature also it is sufficient and activation energy to reach the transition state 1. Then after that it will get converted to product 1. But for the thermodynamic control, you need to require add some energy. You have to give us some energy to the reactant molecule. So that time you have to raise the temperature. So this is a high temperature reaction. At high temperature you can get the thermodynamic product, because the transition state TS2 have a high energy. So for reactant to reach the TS2, it will require more energy. So heating can give that energy, and then it will get converted to product. All of you are clear here? The difference between kinetic and thermodynamic control. Okay. Now we have some examples here. So can we draw the mechanism for this type of reaction? We have discussed in previous class mechanism, right? So here we have diene. 1,3-butadiene and HBr. So HBr is basic or acidic condition. Anyone? We have already discussed its acidic condition. H plus is there. So it will get substitution reaction will takes place. So what will happen? Either it will form the tertiary secondary substituted product or a primary substituted product. So you can see here red one. Here we are getting at minus 80-degree temperature, we are getting the secondary means secondary substituted product, and in case of the primary case we are getting only 20% yield. Why is this the case? Here we have already discussed this type of reaction. HCl was there. Here HBr is there. So first intermediate was carbocation formation, a protonation of this alkene. First protonation was there. Then after that carbocation formation. So protonation transition state was here. So same case here also. Protonation will be done first. Then carbocation formation, which will give the stability. So if you will see the diagram here, I will draw here. Yeah. Suppose these are two axes. This is energy. Okay. Now this is our reactant. Suppose diene, and it's going some reaction condition to reach the transition state 1, where the protonation is done. Means it's concerted reaction, bond breaking and bond making is simultaneously happen at transition state 1, right? Then after getting that point, here what will happen? Carbocation formation will takes place, right? If protonation will done on this side, this bond will get broken. Here carbocation, correct? Carbocation. Now this carbocation is a secondary carbocation. What is the other option? We can do the protonation on any other place. See here. Suppose this is our diene. Now we can do the protonation here also, correct? And here carbocation formation. This is the second case, right? And this is the first case. Now because I have told you in previous class, primary carbocation is less stable compared to the secondary one. Okay, secondary carbocation is more stable, correct? So this is the stable product. Sorry. I am writing intermediate as a product, because if you will get intermediate here carbocation, then it will easily go under product formation to give the P, because carbocation will be trapped by bromine ion, Br minus. Now this is the first case, correct? For this one, this is our first case. What is the second case? Here we have carbocation formation as primary carbon atom. That means it is less stable step. So but here the transition state will go like this way only. See, then I will draw separately, otherwise it will become easier. So here you can see this is a tertiary carbocation intermediate. formation. So this is a tertiary carbocation transition state, right? Intermediate one's transition state. And here I will draw the second case. Because the primary carbocation is unstable, so the energy required to get this carbocation will be high. So that's why the transition state energy will become higher. This is our activation energy. Activation energy for primary formation of primary carbocation is high, correct? But the product which we will get after formation of this carbocation will be more stable compared to the first one. Why it is more stable? So you can see here, in this case, this 80% one product is forming, right? This product is less stable compared to this one. The reason behind this is, this is a, here alkene double bond is di substituted. Here it is mono substituted, means here both the side you have you can see secondary 2 degree substitution. Both the more substituted double bond is here and it is less substituted. So always remember that more substituted double bond is always stable compared to the less stable. So this is a trend I am drawing here. Stability. Okay. So this one is more stable because double bond is more stable. That's why it is a more stable product. The energy is less. That's why we have product energy is very less. So here at minus 80 degree, what happens? First transition state to get the tertiary carbocation was very low because it is a lower hump. Energy required to reach to get the tertiary secondary carbocation was low, less energy. That's why at lower temperature also it quickly jump on this transition state. It crossed this barrier. But where in case of the second stable product transition state, here energy required to make the primary carbocation is more, and because it's a low temperature, so there was no sufficient energy to cross this barrier transition state 2. That's why here we are getting this less stable product as a major product. So this is called a kinetic control product. This is our kinetic product. In kinetic, what happened? Transition state is it depend on transition state energy, and thermodynamic product is based on product stability. So here, because transition state energy is low in is comparison with the second condition compared to the second one. That's why this is a major product. This first will give our major product. Got it? Now the second case. Any question? Okay. So here we have second case at 40-degree temperature, and here you can observe that the condition is inverse, completely inverse. Like here we are getting 80% as a primary substituted product, and here 20% as a secondary substituted product. Why is this the case? As I told you, energy to cross the transition state 2 barrier, it will require more energy. Here we are providing some temperature, some heating, and heating will give the energy to the reactant to reach this transition state 2, and it will cross this barrier to get the more stable product here. No need to draw this hump also, because here we are talking about only one step. This is product. I am writing here product. So you can see here the activation energy for 2 is more. So here we are providing some energy in the form of heat, and it will give the energy to the reactant to reach the transition state 2, and it will get converted to more stable product, right? So this type of product, because it's a stable product, this di substituted double bond is more stable, and because it's a stable product, and it is a thermodynamic control product also. Here we are getting because of heat. So this is a thermodynamic control product, and because it's based on the stability of the product, that's why it's called thermodynamic. Got it? Or any question is there? Any question? Now here we have one more same similar example. I have drawn here transition state. So this is a HCl reaction, as I have already taken this type of example. So carbocation form is under resonance here. It forms in resonance, correct? It can be resonance structure I have discussed in previous class. So this positive charge can move through this double bond. That's why it's in transition state. So this is a resonance form, and this is our transition state. Bond making, bond breaking is taking place simultaneously. So positive charge is on most substituted carbon atom is more stable, and here highest energy of this transition state is because of least stability of this carbocation I have discussed already. And this is our 1,2 addition product, kinetic product, because the transition state energy is low, and here we are getting a 1,4 addition product. That means the transition energy is high. So at 40 degree we are getting this. Suppose at high temperature, and at low temperature, very low temperature, it will react here. So here we are reducing the energy to reach the different type of product, to get the different types of product. So we can play with the temperature to get the desired product. Now we have example here. So the question is here, the most appropriate reaction coordinate diagram for the following reaction is, anyone? Try to solve this question, because this type of question will be there in assignment. So it will help you to solve that assignment and exam also. So here what we will do, we will form chair conformation first. Okay. Now we have CH3 and Br bromine here. Correct. Now H2O will attack from which side? Anyone? Otherwise you can write in other form also. I will write here. CH3, both are same only, because there is no other substituent present on cyclohexane. That's why you can write anyway. So here first H2O will attack from here. So first in first case carbocation formation will takes place, right? Carbocation. So on axial position, this is a SN1 type of reaction. Carbocation formation will take place. Correct? Now after formation of carbocation, what will happen? First, either H2O can attack from upside, or it can attack from downside. But upside is more easily available compared to the downside, correct? So that's why the transition state in this case, wait, yeah, here also the same case is there. So a transition state will become carbocation formation, and carbocation is more stable here, right? It is more stable. So carbocation is stable, tertiary carbocation formation is there. So that's why the transition state 1 will be low in energy, correct? But the second step is axial attack of H2O, OH, sorry, axial attack of OH to give this product which is shown here. I will show both the product. Sorry, I will write here transition state. So this is our intermediate. Carbocation formation is our intermediate, right? It is our intermediate. So now axial attack and equatorial attack, which will be preferable. So because hindrance is less here, it will attack from top side. So what we will get here? OH from top side, H2O. In final we will get OH and CH3, correct? And if it will attack from downside, what we will get? CH3 upside and OH will be on equatorial position, axial and equatorial position. So this is our product A, this is B which is shown here. You can compare with this one, A and B, correct? Now because here we have 1,3 diaxial interaction, you have learned in cyclohexane structure. So 1,3 diaxial interaction is there. So the attack of H2O from axial position will become more, will require more energy compared to the this one. Hindrance, diaxial interaction will show the hindrance. That's why the equatorial position attack will be favorable and required less energy compared to the this one. So that's why the attack from equatorial position will have this low barrier transition state TS1 for A, and this is our product A, and one transition state A. This is transition state B because it's attacking from axial position, which shows the 1,3 diaxial interaction. So this is the product B. So the correct coordinate diagram is first one, this one. Okay. So this is the second question. The correct statement for the given reaction is, you have to find out the correct answer here. First option is product B is major as it is more stable. Second, product B is major because major product as it is formed faster. Then product A is major product as it formed faster, and product A is major product as it's more stable. So which one is the correct answer? This is our reaction. This. Which one? Third. Okay. Okay. Right. Product A is major product as it forms faster. So this is our kinetic product. That's why it's a major product. Got it? The correct option is third. Product A is forming faster because the its transition state energy is low, and it forms faster because kinetic control. And this is our thermodynamic product. I hope all of you are understood this question. Then the next question is, select the reaction coordinate diagram for the reaction with the following criteria. So you have to draw here transition state diagram. So first condition is given here, two-step reaction. The reaction is two-step. So all, all of you know that we will get two hump, one intermediate, two transition state and one intermediate. When where two-step is reaction is that, that means two transition state will be there. So overall delta G energy is less than zero. That means it is a exothermic reaction, because as I told you, enthalpy will be uh, less than 0 and Gibbs free energy will also be less than 0. So this is our exothermic reaction. Got it? So what we have learned for exothermic reaction? Exothermic. Then B is the first step, is the rate determining step. So which will be your rate determining step? The transition state which will have higher energy will be the rate determining step. So in all the cases you can see, in this case transition state TS1 is low in energy. That means it is wrong option, correct? Because the first step is our rate determining step. Here also this is not the case. Now the third condition is that the second step of the reaction is faster than the reverse of the first step. When this will be the case, here the second step of the reaction is faster. Yes, question. Please mute yourself. Yeah. So in third condition, the second step of the reaction is faster than the reverse of the first step. That means product is more stable compared to the reactant. That's why the product formation is faster. Second step is faster and it will not get reverse. Reverse reaction is possible in this case. Suppose this is our product and this is our reactant. So and here intermediate. So according to the third sentence, the second step, that means this transition step reaction is faster than the reverse of the first step, because here it will go reverse and give the product, and here it will give the product. So which one is stable, it will go on that direction. So this is according to the third sentence, product is more stable because reverse reaction is not possible compared to the forward reaction. Forward reaction is much more faster compared to the reverse one. So this is the only case where it is possible, because the stability of product is higher compared to the reactant. That's why it will give the forward direction reaction, and this is your correct option. All of you got this question? How you can draw the transition state diagram in exam also? So this is the trick you have to apply one by one in all in the reaction diagram. Then you can easily find out the transition state energy and determining step. So I hope you can draw other reactions transition state also. Now this is another question. This type of question or concept have discussed by ma'am in the YouTube lecture. You can go and check that lecture also. Lecture 6, 7, 8, 9. I'm covering that lecture syllabus here. So the question is that for the hypothetical reaction A plus 2B plus C is giving D plus 2E, and the overall order is found to be third, right? Third order reaction. So the probable diagram is R. Anyone which will be the correct diagram? First of all, you have to write this way: rate. Your rate is directly proportional to the concentration of reactant, right? B. How you solved it? Can you explain? Yeah. So, but it is a third uh, means it is a third order reaction. So how you can say B is the correct option? Okay, no problem. First, I'm going to explain how you can find out the order of the reaction. Then you will get it. It's rate is always directly proportional to concentration of reactant. All of you know that. Okay. A, B, C. Now order of reaction will be based on is K constant, proportionality constant. Degree of freedom on this concentration. So here, as you can see in first graph, when your dp by dt is increasing, when your reactant concentration is increasing, correct? Your concentration is increases as the rate is also increases. So it is a directly proportional. It's a straight graph. So it is directly proportional. Then A will carry first charge, means when reactant concentration is changing, directly the dp by dt value is also changing, correct? So it will carry one degree of freedom. Now for B here you can see the exponential this way, correct? That means initially it is increasing with concentration slightly, but sudden increase is observed. You can see concentration is here and the rate, sorry, rate is increasing yeah. If you will see this point here, try to understand this one. So here by dt value is too high and reactant concentration is this one, and at same concentration for A1 the dp by dt value is less compared to this one. That means here exponentially increment is observed. Here it will go this direction and this direction. So this is the dp by dt value is increasing exponentially. That's why it will become square. So twice compared to 1. This is the twice rate. So the degree of freedom will become 2 here. And for the C1, you can see here C red line. When you are increasing the concentration of reactant, the dp by dt value is remain same. Product formation value means it is remain as it is. That means the concentration of reactant doesn't affect dp by dt value or rate value. We can say this is our rate law dp by d1. Okay. So when we are increasing the concentration of C, it doesn't affect the rate of the equation. That means C have 0 degree of freedom, 0, right? The change in concentration of C will not affect the rate equation here. That's why it carry the 0. Now you can see total order of reaction is 1 plus 2, that is 3, right? 3. So here the order of reaction will become 3. This will become 1, right? So all of you know which graph diagram is correct. First one only, and why others are incorrect I will explain that also. So here in second case B, as you can see A is directly proportional to rate. Reactant concentration is directly proportional to rate here. That's why A will carry one charge. Degree of freedom is 1, right? Now for B again is the exponential. That means it will be B square. B square. it's increasing rapidly, that's why. So in terms of B concentration, the order of the reaction is 2, that's why I'm writing here 2, and in terms of A concentration it is 1. Now compared to C, we can see C is going this direction, but compared to A it is slow. The reactant concentration is increasing, but the rate is not as much as increasing like A case. That means it is a half, correct. Now here, what will be the order of reaction now? 2 plus 1 plus half. How much it is? 5 by 2, correct. So this is the incorrect option. Now for third one, you can see B is showing exponential increase, that is B square, correct. Here B square we have, but in case of A, we are not getting any change. Line A, correct. When we are increasing the reactant concentration, but the rate is remain as it is, that means it is a 0. And in terms of C also it is 0, because it's a straight line only. So in this case, the order of reaction will become 2 for this diagram. Here, what will be the order of reaction? Yes, 4, correct. So that's why the correct option for third order reaction is A only. I hope all of you are clear here. Okay. So this is for today's lecture. Now I will give a brief summary for today's session. So today we have discussed the reaction coordination diagram, where we have seen the two types of reaction, which one was single step and the two-step reaction. So here we show here that y-axis is our energy, potential energy, and x-axis is our reaction coordinate. So you can see here we have discussed here transition state energy, so reactant energy, transition state and product energy, and the activation energy is the energy required to reach the transition state. In other second step reaction also we discuss the same thing. Energy required to reach the transition state 1, which is called as a activation energy 1, and where the energy required to reach the transition state 2 is called as energy E2. We can denote it by any element E2 also. And the transition state with higher energy is our rate determining step, because it is a slow step. Then we have discussed the examples of reaction coordinate diagrams. So in first example, we have discussed the case where reactant and intermediate are in equilibrium. That means they both have the same energy, and the energy required to get converted intermediate 1 is less compared to the second step. That means the second transition step is a rate determining step, and energy required to reach this transition state will be higher compared to the first transition state. Then in second case we also observe that here also the case is similar, like reactant and intermediate are in equilibration, and transition state first energy is less compared to the transition state 2 energy. So the rate determining step here also is 2, second step, and product is more stable compared to the reactant. Now in the third case, we observe that both the transition states energy are nearly equal, and the intermediate energy are high compared to the reactant and product. So that's why it is a steady state where it can go either this side also or transition state one side also. So it will get converted back to the reactant also, and or it can give the product formation also. So in this type of reaction, the reaction time will be longer, and we will observe both reactant and product formation in the reaction, because it will get back to the reactant also. Now we have discussed the Hammond's postulate. In Hammond's postulate, we discussed that the transition state of a reaction resembles either the reactant of the product, or whichever is a closer in energy. So we have discussed two types of reaction here. The first reaction was exothermic reaction, and in exothermic reaction, the transition state is closer to the reactant than the product. Here you can see, and therefore the Hammond's postulate is an exothermic reaction is showing the, according to Hammond's postulate, the structure of this transition state will be look like reactant. It will resemble the reactant. And in endothermic case, the in endothermic reaction, the transition state is more closer to the product than the reactant, and therefore according to the Hammond's postulate, in an endothermic reaction, the transition state resembles the product, and the energy of the product will be high compared to the exothermic reaction, because here enthalpy, here delta H enthalpy will be greater than 0, and in exothermic reaction the delta H enthalpy is less than 0. So the Gibbs free energy relation will also remain the same. For this case, Gibbs free energy will be less than 0, and here also Gibbs free energy will be less than 0. Okay. Now we have discussed the example for Hammond's postulate. Here we have seen the formation of transition state and product formation. So as we can see here, we have alkene, and then the protonation is taking place. So protonation is our transition state. So because protonation on primary carbon atom is taking place to give the tertiary carbocation, that's why this transition state is more stable. That's why here we are getting less hum. In second type of possibility we have discussed later. So here we have observed that carbocation formation is taking place, and it's a stable form compared to the transition state 1. That's why it's going down, but the energy of this transition state is higher compared to the reactant, because alkene is more stable. And then this proton carbocation will get will be attacked by the nucleophile Cl- to give the desired product. So this carbocation will be trapped by Cl- to give corresponding product, and the transition state energy will be less compared to the transition state 1, because it's both are stable species. That's why. Then we have discussed the kinetic versus thermodynamic control products. So we have observed that the kinetic product is the product that forms faster, and the thermodynamic product is the product that is more stable. So here we observe two type of cases. In green graph, you can see the product is less stable, but the intermediate, or not intermediate, transition state and energy required to reach the transition state is low. That means it is a fast step. So because it's becoming faster, that's why it is a kinetic control. And kinetic control reaction are depends on the activation energy of reactant, that means transition state energy. So the transition state energy is low, that means it is a kinetic control reaction. And in case of the thermodynamic product is more stable here, but the energy required to reach the transition state is very high. That's why it is a slow reaction, and it's a thermodynamic control product. Then we have discussed here both type of product, kinetic and thermodynamic. So we have seen here we have one three uh, butadiene, 1,3-butadiene. Here, when the protonation is taking place in this type of reaction, so it can either done on primary carbon or on tertiary carbon. So we have both the cases. We discuss here both the cases. Here we are getting carbocation formation at secondary carbon. Here on primary carbon. So because the primary carbon is less stable compared to the secondary carbon, so the transition state will be higher. compared to the primary one, and this is a transition state for primary carbon. Sorry, this is the secondary carbon. This is transition state for the primary carbon. So transition state for the primary carbon will always be higher because primary carbocation is less stable. Tertiary carbocation is more stable. Correct? So, but the product formation, when we'll talk about the product formation, we'll see that this primary substituted product is more stable because here double bond is di-substituted. Here double bond is mono-substituted. So, the product, this one is more stable, but we are getting in less yield, and this is high yield because of the temperature. And the temperature, sorry, because of the temperature and transition state. So as all of you know that transition state for the tertiary carbocation is low in energy and it will quickly give the product. That's why at low temperature also it will quickly cross this barrier to give the product, kinetically controlled product. And in the second case, to cross this barrier, which is transition state 2, the energy will require more. So at more temperature, high temperature, we will provide some energy in the form of heat to the reactant. Then it will cross this transition state 2 barrier to get the thermodynamically stable product P. Correct? So you can write in one graph also. Instead of writing in two graphs, you can write in one graph. Product, reactant. Other option is this is a product. Got it? So this is our thermodynamic product. This one. This one is kinetic one. Okay. So I hope all of you clear in this example also. Then we have discussed with HCl example. Here also we have discussed the same thing, stability of transition state, and we observe that the transition state with secondary carbocation is more stable transition state and required less energy uh, to reach the transition state. That's why it happens at low temperature and give the secondary substituted product. And in case of this one, primary carbocation energy is high, so it required high temperature to reach the transition state, and it will give thermodynamically control major product. Then we have discussed the coordinate diagram here, reaction coordinate diagram. So we have observed that here we have reactant, not intermediate, reactant R, and either it can go this B formation or A product formation. So depending on the stability, we observe that 1,3 diaxial interaction was there after carbocation formation. So we observe that axial attack will be less favorable compared to the equatorial. So the energy required to attack from axial side will be more compared to the equatorial. So that's why this is the high energy required more for axial attack. So and this is energy required less for equatorial attack. That's why this is the correct option. Okay. Now we have seen here the another question. The correct statement for the given reaction is, we have observed that the product A is a major product as is formed faster. So you can see here we have reactant here, and the transition state for product A formation is less compared to the energy of transition state is less compared to the transition state 2, right? It will require less energy. Sorry. That's why your A product is major and the reaction is done at 0 degree temperature. You can see here it is at 0 degree, means low temperature. At low temperature it will cross the low energy barrier only. If you will increase the temperature, then you will get the B as a major product. Here you will get the A as a major product because it is on 0 degree to RT. If you will increase the temperature, then reactant will cross this transition state to energy and it will give more stable product B. Okay, so always remember the reaction condition also. I forget to explain this one. So I hope all of you got this one. Now the next question is, select the reaction coordinate diagram for the reaction with the following criteria. So here we have discussed the different criteria. The first one was two-step reaction. So we will observe that here all the options are have two-step reaction diagram only. But here we have observed that overall delta G energy is less than 0. That means Gibbs free energy is less than 0. It shows the stability of the product and exothermic reaction. So in exothermic reaction, product is more stable compared to the reactant. So in all the cases, you will observe these two cases have the product stability, more stability, right? But in the second point, we observe that the first step is a rate determining step. That means the transition state first will have the high energy compared to the transition state 2. So the higher energy transition state are these two only, right? First and second one, these two. So that means these two are cancelled. With 2 points also you can find out the correct answer, because in earlier first point, with first point we got that these two can be a correct answer, but in by the second point we get this is a wrong option. That means we can finally write this answer also, but third point also you can use for better probability for writing the better diagram. So the third point is, the second step of the reaction is faster than the reverse of the first step. This is also the same meaning. That means your product stability is more compared to the reaction. This Gibbs free energy is also showing the same thing, and here it is also the same thing. That means this is your correct option. Sorry. Then in this question we have discussed the rate of reaction. So the question was for the hypothetical reaction A plus 2B plus C giving a D plus 2E. The overall order is found to be 3 and the probable rate diagram will be our A1. How we got this A diagram? We observe that rate is directly proportional to the concentration of A, B and C. So as our concentration is increases, the rate of A is also increasing here. That means it is a indirect relation. So here the degree of freedom or of A reactant will become 1. That means the reaction rate of reaction in terms of A is first order reaction, because it's changing with the reactant concentration constantly, equally. It is a direct proportional ratio. Now, the second case for B, you can see it is a exponential. It's giving a exponential. That means the reactant concentration is increases as the reactant concentration is increases, the rate is increases rapidly. That means it is a exponential, and it will give the 2 as a degree of freedom. That means in terms of reactant B, the order of the reaction is 2. While in case of C, we observe that as the concentration of C is increases, there is no change in rate equation. It is remain unaffected. That's why here we will get the 0 order of reaction in terms of concentration of C, and we will get the third order reaction for this diagram. While talking about the second one, we observe that here A is giving the order 1. Here we have written order 1, and B is giving order 2 exponentially because it's giving an exponential increment, and C is increasing slightly but not the 0. It giving some value. That's why it is a half. So if we will calculate this one, we will get pi by 2 as a order of reaction, which is incorrect according to the question. In question they have mentioned the order of reaction should be 3. So this is a wrong option. Then third one is also a wrong option. Why? Because B and C are independent of the rate equation. That means it is the concentration is increases as the rate is remain unchanged. So that's why the here the order of reaction for B and C will become 0. In terms of B and C will be, sorry, no, A and C. Sorry for the mistake. This is our B. This is our B. So the order of reaction is 2. In third case also we observe that the order of reaction is 4 because we are getting here 2 exponential graph and one C concentration is 0. The change in rate is 0 here. That means it has a 0 degree of freedom and it have a fourth order of reaction. So I hope all of you are clear in today's lecture. If you have any doubt, any question, you can ask me now. Anything is there? No question. Okay. Thank you so much for your kind attention. Next Saturday again we will have a live session from 3 to 5 o'clock. So please join and we will discuss the next topic. Thank you.